Welcome to this video on solving LeetCode problem number 2101, Detonate the maximum bombs. In this problem, we'll explore an exciting challenge involving graph-based techniques and recursion to maximize the number of detonated bombs. Let's dive in and break it down step by step. In this problem, you are working with a list of bombs, where each bomb is described as an array, x, y, r. Here, x and y represent the coordinates of the bomb on a 2D plane, and r is the radius of the bomb's blast. The goal is to determine the maximum number of bombs that can be detonated through a chain reaction, starting with just one bomb. A bomb can trigger another bomb if the distance between their centers is less than or equal to the radius of the first bomb. This relationship is defined mathematically by the inequality x I x j caret 2 plus y I y j caret 2 equals r I caret 2. Using this, you must simulate how a single detonation can cause a chain reaction, potentially triggering multiple bombs. The input is a 2D list of integers representing the bombs, and the constraints ensure that the number of bombs is manageable, with their coordinates and radii bounded within reasonable limits. The output is a single integer representing the maximum number of bombs that can be detonated in such a chain reaction. The task requires you to return an integer that represents the maximum number of bombs that can be triggered in a single chain reaction. Let's consider a few examples to clarify. In the first example, the input is bombs equals 2, 1, 3, 6, 1, 4. If you start by detonating bomb 0, located at 2, 1, with a radius of 3, it can trigger bomb 1 because the distance between them is 4, which is within the blast radius. Similarly, if you start with bomb 1, it can trigger bomb 0. In either case, both bombs detonate, so the maximum number of bombs triggered is 2. This illustrates how the chain reaction works when the bombs are within each other's blast radii. Now let's look at another example with bombs equals 1, 1, 5, 10, 10, 5. Here, bomb 0 is located at 1, 1, with a blast radius of 5, and bomb 1 is at 10, 10, with the same radius. The distance between these two bombs is too great for either to trigger the other. If you choose to detonate bomb 0, only bomb 0 will explode, resulting in one detonated bomb. Similarly, starting with bomb 1 will only detonate bomb 1. Since no chain reaction is possible, the maximum number of bombs detonated in this scenario is 1. In a third example, the input is bombs equals 1, 2, 3, 4, 5, 3, 7, 8, 3. Here, each bomb has a radius of 3, but the distances between all the bombs are too large for any of them to trigger another. As a result, no matter which bomb you choose to detonate first, only that bomb will explode. The chain reaction stops immediately because none of the other bombs are within range. Therefore, the maximum number of bombs detonated in this case is 1. This example highlights a scenario where the bombs are too far apart to interact, limiting the chain reaction to just one bomb. To summarize, there are a few key scenarios to consider. If there is only one bomb, the result will always be 1 since no chain reaction is possible. If multiple bombs have the same coordinates but different radii, their ability to trigger one another depends on whether their radii overlap. When bombs are disjoint, meaning they are too far apart, the maximum detonated bombs will be 1. On the other hand, if all bombs are close enough to trigger one another in a complete chain reaction, the result will be the total number of bombs. These edge cases help clarify how the problem handles different configurations of bombs and their blast radii. To solve the problem of detonating the maximum number of bombs, we can think of it as a graph traversal problem. Each bomb acts as a node, and there are directed edges to other bombs if they fall within the initiating bomb's blast radius. A brute force approach to this problem involves simulating the detonation for every bomb. The steps include creating edges between bombs based on their blast radii, and then for each bomb, performing a traversal like DFS or BFS to count all the bombs that can be triggered. While this approach is straightforward, it has a significant drawback: its time complexity is O(n cubed), which includes constructing edges and performing graph traversal for every bomb. This makes it impractical for larger inputs, like when the number of bombs is in the order of 10,000 or more. The optimized approach improves on the brute force method by reusing the graph structure and eliminating redundant computations. Instead of reconstructing and re-exploring the graph for each bomb, we pre-compute an adjacency list that maps each bomb to the bombs within its blast radius. From there, we use DFS or BFS to explore reachable nodes. This reduces the overhead significantly, as graph construction remains O(n) squared, but traversal from each bomb is now O(n), leading to an overall complexity of O(n) squared. This is a big improvement over the brute force method. Additionally, this approach is practical for input sizes up to 10,000 bombs, making it efficient and scalable for most constraints while maintaining simplicity in implementation. An alternative to DFS or BFS is the union find approach, which uses the concept of connected components. Here, we treat the graph as a collection of these components, where each component represents a group of bombs that can trigger one another. Using union find, we can efficiently group bombs by checking pairwise interactions and uniting those that fall within each other's blast radius. Once we've grouped all bombs, the size of the largest connected component tells us the maximum number of bombs that can be detonated. While this method is efficient and scales well, it involves additional complexity in implementation, particularly in managing and updating the disjoint set structure. Furthermore, it still requires O(n) squared for the pairwise checks, meaning its overall complexity is similar to the optimized DFS/BFS approach. The optimized graph-based approach with DFS or BFS was chosen as the strategy for this problem. This decision was based on its balance between simplicity and efficiency. The problem is fundamentally about determining reachability in a graph, and DFS or BFS are well suited to this task. By using an adjacency list, we minimize redundant distance calculations, and the traversal itself explores all reachable nodes from a given starting bomb efficiently. While union find is a valid alternative, it introduces unnecessary complexity for this specific problem because we don't explicitly need to track connected components. The brute force method, on the other hand, is computationally prohibitive for large inputs. Thus, the graph-based DFS/BFS approach strikes the right balance, offering a clean and effective solution within the constraints. To summarize, the solution involves two main steps. First, constructing a graph to represent bomb interactions, which requires O(n) squared time, and second, performing DFS or BFS from each bomb to calculate the maximum number of detonations, which takes O(n) per starting bomb. The total time complexity of O(n) squared is efficient enough for the problem's constraints, and this approach is straightforward to implement and understand. By avoiding redundant computations and leveraging graph traversal techniques, we achieve a practical solution that balances speed and simplicity, making it well suited to solve the problem effectively. To solve the problem of detonating the maximum number of bombs, we first need to understand its structure. Each bomb is defined by its location, x, y, and a blast radius r. When a bomb detonates, it can trigger other bombs if they fall within its blast radius. The challenge is to determine the maximum number of bombs that can be set off if we start from any single bomb. To approach this, we can frame the problem as a graph traversal task. Here, each bomb is represented as a node, and a directed edge is drawn from one bomb to another if the second bomb lies within the detonation range of the first. This relationship can be determined mathematically using the equation x_i(x_j) caret 2 plus y_i(y_j) caret 2 equals r_i caret 2. By creating this graph, where nodes represent bombs and edges represent possible triggering relationships, we can leverage traversal algorithms to explore the reach of each bomb efficiently. The first step in solving the problem is to construct the graph representation. To do this, we initialize an empty adjacency list. Then, for each pair of bombs, I, j, we calculate the squared Euclidean distance between them. If the squared distance is less than or equal to the square of the blast radius of bomb I, it means bomb j is within the detonation range of bomb I. In that case, we add j to the list of neighbors for I in our adjacency list. This process involves comparing every pair of bombs, resulting in a time complexity of O(n) squared, where n is the total number of bombs. Once the graph is built, the next task is to traverse it. For this, we define a helper function to perform either depth-first search, DFS, or breadth-first search, BFS. The key goal of the traversal is to explore all bombs that can be reached from a given starting bomb. During the traversal, we maintain a visited set to keep track of which bombs have already been detonated, ensuring no bomb is counted more than once. The traversal counts the total number of bombs that can be triggered starting from the initial bomb. Both DFS and BFS are suitable for this task, but we use DFS due to its straightforward recursive implementation. After defining the graph traversal function, the next step is to iterate over all bombs and calculate the number of bombs that can be detonated when each one is treated as the starting point. For each bomb I, we perform a DFS and count the number of reachable nodes in the graph. As we progress, we keep track of the maximum number of detonated bombs across all starting points. The overall time complexity remains O(n squared), because for each bomb, we may traverse all other bombs during the DFS. Once we've iterated through all the bombs, we return the maximum count as our result. This approach highlights several key insights. First, representing the problem as a directed graph simplifies the solution by clearly encoding the triggering relationships between bombs. Second, both DFS and BFS are valid traversal choices since our goal is simply to count reachable nodes. However, DFS is chosen here for its recursive simplicity. Third, to optimize performance, we use squared distances instead of calculating the exact Euclidean distance, avoiding unnecessary square root computations. Finally, the algorithm handles various edge cases, such as bombs with zero radius that can only trigger themselves, isolated bombs that do not connect to any others, and dense clusters where chain reactions or circular dependencies occur. To implement the solution efficiently, we rely on two key data structures. The first is an adjacency list, which represents the graph and is memory efficient compared to an adjacency matrix, particularly for sparse graphs. The second is a visited set, used during the DFS to ensure we do not traverse the same node multiple times. When analyzing the complexity, the graph construction step takes O(n squared) time because we compute distances for all pairs of bombs. The DFS traversal takes O(n) per starting bomb in the worst case, leading to a total time complexity of O(n squared) for all bombs. In terms of space, the adjacency list requires up to O(n squared) in the worst case if every bomb can trigger every other bomb. Additionally, the visited set requires O(n) space during traversal. Overall, while the approach has a quadratic time complexity, it is efficient and well suited to the problem's constraints, particularly given the manageable input sizes typically encountered in competitive programming. By structuring the problem as a graph traversal, we achieve clarity and efficiency in finding the maximum detonatable bombs. Here, we start by importing the necessary module, deq, which will help us implement a breadth-first search, or BFS. Inside the solution class, we define the maximum detonation method, which will determine the maximum number of bombs that can be detonated in a chain reaction. First, we calculate the total number of bombs, n, and then create an adjacency list called graph. This list will represent which bombs are within the blast radius of each other. We initialize it as an empty list for each bomb. Next, we iterate through each bomb using a nested loop. For a given bomb I, we extract its coordinates and radius, and then compare it with every other bomb j. If the distance between the two bombs is less than or equal to the radius of bomb I, we add bomb j to IS adjacency list. This is done using the distance formula, x1, x2, 2 plus, y1, y2, 2, and checking if it's within or 1, 2. By the end of this step, we have a graph that maps each bomb to all other bombs it can directly detonate. We then define a helper function, BFS, to perform a breadth-first search starting from a given bomb. This function will help us count how many bombs can be reached from the initial one. Inside BFS, we initialize a visited set to keep track of the bombs we've already processed in a queue for our BFS, starting with the given bomb. The first bomb is marked as visited, and we begin exploring its neighbors. Now, inside the BFS function, we iterate through the queue as long as there are bombs left to process. For each bomb, we retrieve its neighbors from the adjacency list. If a neighbor hasn't been visited yet, we add it to the visited set and enqueue it for further exploration. This ensures that we traverse all bombs reachable from the starting bomb. Once the queue is empty, meaning no more bombs can be detonated in the chain reaction, the function returns the total number of visited bombs, which represents the reach of the chain reaction starting from that bomb. With the BFS function ready, we now calculate the maximum number of bombs that can be detonated. We iterate through each bomb and call BFS on it to determine the reach of a chain reaction starting at that bomb. Using the max function, we keep track of the highest number of bombs reached across all possible starting points. Finally, the method returns max_detonated, which represents the maximum number of bombs that can be detonated in a single chain reaction. This completes our Python implementation of the solution. Here, we begin implementing the solution by importing the necessary packages and defining the class solution with the method maximum_detonation. This method takes a 2D array of bombs as input, where each bomb is represented by its x and y coordinates along with its blast radius. The first step is to determine the number of bombs, which we store in the variable n. Next, we construct an adjacency list to represent a graph, where each bomb is treated as a node, and an edge connects two nodes if one bomb is within the blast radius of the other. To build this graph, we iterate through each pair of bombs. For each pair, we calculate the squared distance between their centers to avoid floating point precision issues. If the squared distance is less than or equal to the square of the blast radius of the first bomb, we add the second bomb to the adjacency list of the first. This creates a graph that captures the detonation reach of each bomb. Finally, we define a helper function BFS to perform a breadth-first search and count all reachable nodes, which will help us determine the maximum chain of detonations. The BFS helper method begins by initializing a queue and is set to track visited nodes. Starting with the given bomb, we add it to both the queue and the visited set. Using a while loop, we process each bomb in the queue by polling it and visiting all its neighbors from the graph that haven't been visited yet. For each unvisited neighbor, we mark it as visited and add it to the queue, ensuring we explore all reachable bombs. Once the queue is empty, the size of the visited set represents the total number of bombs that can be detonated starting from the initial bomb. After defining the BFS method, we iterate over all bombs, treating each as a potential starting point for detonation. For each bomb, we calculate the number of bombs that can be detonated using the BFS method and update the maximum count using math.max. Finally, the function returns the maximum number of bombs that can be detonated, which is the solution to the problem. To begin, we are given a simple case with two bombs. These bombs are represented by their coordinates and their blast radius. The first step is to pre-compute an adjacency list to determine which bombs can trigger each other. For bombs 0 at 0, 0, with a radius of 2, we calculate the distance to bombs 1 at 2, 0. Using the distance formula, we find the distance is exactly 2, which is within the blast radius. So, we add bombs 1 to the adjacency list of bombs 0. Similarly, for bombs 1 at 2, 0, we check if it can trigger bombs 0. The distance again is 2, so bombs 0 is added to the adjacency list of bombs 1. The final adjacency list is 1, 0. Next, we perform a breadth-first search, BFS, to simulate detonating the bombs. Starting with bombs 0, we initialize the visited set in queue, marking 0 as visited and enqueuing it. We then process bombs 0's neighbors, adding bombs 1 to both the visited set and the queue. By the end of this traversal, the detonation count is 2. For the BFS starting with bombs 1, we follow a similar process. We initialize the visited set with 1 and enqueue it. As we process bombs 1, we add its neighbor, bombs 0, to the visited set and queue. After traversing both nodes, the detonation count is again 2. Comparing the results of both BFS runs, the maximum number of bombs that can be detonated is 2. Next, we explore a case where no bombs can trigger each other. Here, the input consists of two bombs with coordinates 0, 0, and 5, 5, each having a blast radius of 1. First, we pre-compute the adjacency list. For bombs 0, the distance to bombs 1 is calculated as SQRT, 50, which exceeds the blast radius of 1. Similarly, the distance from bombs 1 to bombs 0 is also greater than 1. Therefore, neither bomb can reach the other, and the adjacency list becomes. With the adjacency list ready, we move on to the BFS traversal. Starting with bombs 0, we mark it as visited and enqueue it. Since bombs 0 has no neighbors in the adjacency list, the traversal ends with a detonation count of 1. Similarly, for bombs 1, we initialize the visited set in queue, but no additional nodes can be visited, resulting in a detonation count of 1. Comparing the results from both BFS runs, the maximum detonation count in this case is 1. This example highlights a scenario where the bombs are too far apart to trigger any chain reactions. Now, let's examine a more complex example featuring a chain reaction. Here, we have 3 bombs arranged such that each can trigger the next. The bombs are located at 0, 0, 3, 0, and 6, 0, each with a blast radius of 3. We start by pre-computing the adjacency list. For the adjacency list, we first analyze bombs 0 at 0, 0. The distance to bombs 1 at 3, 0 is exactly 3, which is within the blast radius, so we add bombs 1 to its adjacency list. Next, for bombs 1 at 3, 0, it can trigger both bombs 0 and bombs 2, so we add both to its adjacency list. Finally, bombs 2 at 6, 0 can trigger bombs 1, so we add it to its adjacency list. The final adjacency list is 1, 0, 2, 1. With this list, we begin the BFS traversal. Starting from bombs 0, we mark it as visited and enqueue it. As we process its neighbor, bombs 1, we add it to the visited set and enqueue it. Continuing the traversal, bombs 1's neighbor, bombs 2, is also added to the visited set and queue. Finally, we process bombs 2, which has no additional neighbors. This BFS traversal results in a detonation count of 3. Performing similar BFS traversals starting from bombs 1 or bombs 2 leads to the same result, as all bombs in this configuration are reachable from any starting point. Therefore, the maximum number of bombs that can be detonated in this example is 3. This demonstrates how chain reactions can significantly amplify the number of detonations. By carefully analyzing the adjacency list and performing BFS for each bomb, we can systematically compute the maximum detonation count for any given set of bombs. To analyze the time complexity of this problem, we can break it down into 2 main components: graph construction and BFS traversal. First, let's consider the graph construction process. We iterate through all possible pairs of bombs, checking if one bomb lies within the blast radius of another. This involves calculating the squared distance between the 2 bombs and comparing it to the square of the blast radius. Since there are n bombs, this results in n times n iterations, giving us a time complexity of n squared for graph construction. Next, for each bomb, we perform a BFS traversal to determine the number of bombs that can be detonated starting from that bomb. In the worst case, where the graph is dense, BFS might visit all n nodes, and since BFS is performed for each bomb, this requires n BFS traversals. Each traversal is n, so the total BFS cost also becomes n squared. Combining these 2 components, we find that the overall time complexity is dominated by n squared. When we add up the time complexities of graph construction and BFS traversal, we get n squared plus n squared, which simplifies to n squared. Now, let's examine the space complexity. The primary contributors to space usage are the graph, the BFS queue, and the visited set. For the graph, we use an adjacency list representation. In the worst case, where each bomb can reach every other bomb, the adjacency list will store n nodes, each with n1 neighbors. This requires n squared space. For BFS, both the queue and the visited set store nodes during traversal. In the worst case scenario, where all n bombs are visited during a traversal, these structures require n space. Since the adjacency list dominates the space usage, the overall space complexity is n squared. Now, let's look at the best, average, and worst cases. In the best case, no bomb can reach any other bomb, resulting in a sparse graph. BFS terminates quickly, but graph construction still takes n squared, so the overall complexity remains n squared. In the average case, some bombs can detonate a subset of others. While BFS may be less expensive than in the worst case, graph construction still dominates, leading to n squared. In the worst case, every bomb can detonate every other bomb, forming a fully connected graph. Both graph construction and BFS reach their maximum complexity of n squared. Comparing this to a naive approach where we simulate all possible subsets of bombs, the naive solution would involve checking 2 to the power of n subsets, resulting in an exponential time complexity of 2 to the power of n. The optimized approach, on the other hand, constructs the graph and uses BFS to calculate connected components, achieving a polynomial time complexity of n squared, which is a significant improvement.
To mathematically prove the big O complexities, let's revisit the two main components. First, graph construction involves a double loop iterating over all pairs of bombs.
Since there are n bombs, this results in n times n iterations, which is O, n squared.
Next, BFS traversal visits all reachable nodes for each bomb.
In the worst case, this means visiting all n nodes during each of the n BFS calls, resulting in n times n iterations, which is also O, n squared. Combining these, we add the complexities of graph construction in BFS to get O, n squared plus n squared, which simplifies to O, n squared. Therefore, the overall time complexity of the solution is O, n squared. For space complexity, the adjacency list representation requires O, n squared, in the worst case, which dominates the space usage. Thus, the space complexity is also O, n squared. One of the most common mistakes in this problem is incorrectly calculating the distance between two bombs. Instead of using the Euclidean distance formula, which is SQRT, x2, x1, caret 2 plus, y2, y1, caret 2, some mistakenly use the Manhattan distance, which is at x2, x1 plus, y2, y1. Since the problem involves a circular range of impact, the Euclidean distance is required to determine whether one bomb can trigger another. Another frequent pitfall is ignoring chain reactions. This problem isn't just about checking which bombs are directly reachable, but also about recursively or iteratively simulating the entire chain of explosions using methods like DFS or BFS. Missing these chain reactions can significantly underestimate the number of detonated bombs. Finally, an inefficient approach to graph construction can also cause problems. While brute force, such as checking all pairs of bombs, may work for smaller inputs, it's not optimized. Leveraging geometric considerations or other constraints from the input can help speed up graph creation and improve performance.
Another challenge comes with handling floating point precision.
Using SQRT directly to compare distances can lead to subtle precision errors. A better approach is to compare the squared distances instead, avoiding unnecessary computations while also improving numerical stability. Additionally, some solutions fail to account for isolated bombs, those that do not trigger any other bombs. Assuming all bombs are interconnected can lead to incorrect results or unnecessary computations. It's important to explicitly handle these isolated cases, ensuring that the solution remains accurate and efficient even in edge scenarios. This problem can be effectively modeled as a directed graph, where each bomb represents a node, and a directed edge exists if one bomb can detonate another. A solid understanding of graph traversal techniques, such as DFS and BFS, is essential to solving the problem. Simulating how the chain reaction propagates is a critical step, and it's helpful to evaluate the pros and cons of DFS versus BFS.
For instance, DFS might be more memory efficient for certain inputs, while BFS can be easier to implement iteratively.
Optimization is another key topic. Discussing the time complexity of the solution and how graph construction impacts runtime is important. For instance, constructing the graph in O, n squared, time is acceptable when the number of bombs is capped at 100, as per typical constraints. Being able to articulate these trade-offs and how the constraints justify them demonstrates a strong grasp of the problem. Several related problems from LeetCode can help build the necessary skills to tackle this one. For example, LeetCode 130, Surrounded Regions, uses similar BFS or DFS traversal techniques. LeetCode 200, Number of Islands, focuses on identifying connected components, which is conceptually similar to tracking chain reactions here.
LeetCode 323, Number of Connected Components in an Undirected Graph, also involves graph traversal, though in an undirected context.
Lastly, LeetCode 207, Course Schedule, deals with directed graph traversal and dependencies, akin to the chain reactions in this problem. Alternative approaches include constructing an adjacency list where each bomb points to the bombs it can trigger, then using BFS or DFS to calculate the total number of detonations per bomb.
While simple to implement, this approach may be slower for large graphs.
Pre-computing squared distances is another option, as it avoids precision errors and reduces computational overhead, though debugging squared comparisons can be less intuitive. For further optimization, spatial partitioning techniques like quad trees or spatial hashing can be employed. These methods allow for efficient range queries when determining which bombs are within the detonation radius of others. By partitioning space, you can significantly reduce the time spent constructing the graph, especially in cases with a large number of bombs. However, this added efficiency comes at the cost of increased implementation complexity. Such methods are generally most useful when the input size is large, and the constraints demand a more scalable solution. In conclusion, we tackled the problem detonate the maximum bombs using graph traversal techniques like BFS or DFS. This problem is a great example of how graph theory can be applied to real-world scenarios. Be sure to practice similar problems to strengthen your skills. Thank you for watching, and don't forget to like and subscribe for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!